All right. Okay, so let's look at this, right? So we're looking at discriminant analysis. So discriminant analysis is another form of a classifier. Okay, so you're trying to identify. You have you have data points, right? You're training data, and they belong to one of the two classes, and you can generalize it to more than two classes. But here we are going to assume that you have two classes, and you want to be able to learn from that training data set, and then when I give you a new example, you want to say which class it belongs to, right? It's a classic machine learning problem. So we are going to take an example in which your data, so each x, right? Each x belongs to a two-dimensional space. So which means that each x can be represented using two bits, two elements, right? And they can be continuous. That's why there's an R here, right? So let's say for your training data, now typically the training data that will be given to you will be like this, right? So it will be x1, x2, and then there'll be the class. Then the second example, class, and so on, right? But since we are assuming that they're two-dimensional and they belong to real number space, right? Which means that we can denote them on this two-dimensional coordinate space, right? So each point now can be mapped here, yeah? So let's say the data looks like this, and this is very similar to what we looked in perceptrons as well, is let's say your data looks like this. So all the positive, so C is either 0 or 1, right, or positive or negative. So I'm going to denote all the C's with a black plus sign, and all the negative examples with a red negative sign. Now you want to learn from this. I guess you can't see the color. Okay, that's fine. To learn from this so that when I give you a new example, x star, I want you to tell me what is C x star going to be, right? Which is the label. Yeah, and then of course, since this is a probabilistic classifier, I would not ask directly for C x star, but I would ask what is the probability of, let's call it y, right? That's the label. What is the probability of y star to be 1 given x star, and what is the probability of y star to be 0 given x star, right? So this is where it starts differing from perceptrons, because in perceptrons you would directly tell if it's 1 or 0. Here I would get probabilities, right? So that's the probabilistic notion of a classifier. So that's what we have to learn. So I've just set up the stage for discriminant analysis, right? So in discriminant analysis, what you assume is that each class, right, the points belonging to each class come from a Gaussian distribution, all right? So that's your inductive bias that you're putting in. However, the parameters of the Gaussian distribution, there will be two Gaussian distributions now. The parameters will be different, right? They will, so remember that, so assumption or the inductive bias is that points in class C equal to 1 and points in class C equal to 0 belong to a Gaussian distribution. All right, two different Gaussian distributions, not the same Gaussian distribution, of course, right? Sometimes when we talk about a univariate Gaussian distribution, when there is only one variable, we also refer to it as a normal distribution. So don't get confused if you see those two terms. But here we are going to talk about Gaussian distribution. All right. So there will be one distribution. So let's call it D1. It will have two parameters, right? Mu1 and sigma1, right? Because each distribution has each Gaussian distribution has two parameters: the mean vector and the sigma1, and D2, which will be mu2 and sigma2. All right. So our job, the learning phase, is to learn these parameters. All right. And we have already seen in the last class how to learn the parameters. So that becomes a parameter estimation problem. And using MLE, so you can you can learn these things. So the learning task is given training data, right? Learn mu1, sigma1, mu2, and sigma2, right? And once you have that, then what you do is you apply this equation. So let me switch to the slides here. All right. So if you look at this equation, right, so you want to compute what is the probability of y equal to 1. That's a standard Bayes rule implementation. So all you need is you have computed this, and you know this, and then you compute the probability of y equal to 1. All right? Any questions so far? Okay, good. So now, so we have already looked at the learning task. So learning task is easy, right? What you do is you look at only the negative examples and you try to estimate the mean and variance, right? And then mean and covariance matrix. And then you look at only the positive examples and you compute the mean and covariance, right? And we have already seen that if you are using the MLE estimates, then so if using MLE procedure, right? Then mu1, the mean of distribution 1 will be nothing but the sample mean, right? So you take all of these values and take a mean of it, right? So let's say sample mean of all the x's, summation of all the x's. Now each x of I is a vector, right? I equal to 1 through n1, but only those which where x of I, where c of x of I is equal to 1, which essentially this is a mathematical way of saying take the sample mean of these plus points. And same way you can compute the covariance matrix, which will just be the sample covariance matrix. So that will just be x of I minus what is that, mu of 1 times x of I minus mu of 1 transpose, right? And summation all over all I. Right? So if you look at this, right, this is now each x of I is a vector, which means that mu will also be a vector, right? Because if you think of geometrically, mu, the mean is some point over here, right? So this somewhere here, this is where your mu1 lies, right? So that is also a two-dimensional point, right? Same way here, this is where the mu2 would lie, somewhere in the middle. Right? So each one of these mu's is a vector, and if you think of this sigma, now this is a covariance matrix. So so the covariance matrix will actually be a matrix, right? Because you're taking this quantity is going to be a vector. In this case, it's going to be 2 cross 1, and this is going to be transpose of that. So when you multiply them, you get a 2 cross 2 covariance matrix, right? So I assume that you are familiar with what a two-dimensional Gaussian distribution is, right? So essentially, if you look at it, so a two-dimensional data coming from a two-dimensional Gaussian distribution can look like this, right? So this is x1, this is x2. So the mean is over here, that's the mean. And what the covariance matrix tells us, this covariance matrix will actually have 4 values, 1, 2, 3, 4. These values, the diagonal values denote the variance along each dimension, right? So that tells you, okay, this value tells how wide is this distribution going to be in this direction. This tells you how wide is it going to be in this direction. And then these values, the off diagonal values, tell you the correlation. So it tells you how skewed this is going to be. So for example, if both of these are equal and these are 0, all right? If let's say both of these are 1 and these are zeros, then it will look like a perfect circle, okay? However, if you change it, and if you make one of these values 10 and 1, 0, 0, then it will look like an ellipse, because now the variance along this is higher and variance along this is lower, right? Then, and the same way, if you increase this, it becomes elongated in this direction. Now, if you have some, let's set these to 1, but let's say these are, and this has to be symmetric. The covariance matrix is always symmetric, right? Because if you look at the way how the covariance matrix is computed, these values will always be symmetric. So if you look at this vector, or this matrix, then what it will look like is, because basically what this is telling you is what is the correlation or covariance between these two dimensions. So if it is positive, non-zero, then it's going to be elongated like this, right? So these are the different shapes. However, with the MLE estimate, you can automatically learn this directly from the data itself using these equations, okay? So that is the training phase. Now you have done the training phase. So after you have done the training phase, you know what is this, right? And then you can apply the equation that I showed you earlier, which is the probability of y star to be 1 given x star will just be, p of y star to be 1, which is the prior probability of 1, class 1, and then the conditional distribution. So x equal to x star given distribution 1. So that is just the normal density over here divided by the denominator, which is the sum of all classes, right? So this is easy. Now we are going to look at what does it mean geometrically, okay? So geometrically, what it means is that this is your data, right? If this is your data, and I give you a new point, let's say the new point is here. Now we don't know what its class is, right? So this is my x star. So essentially, what this equation does is over here, not this one. What this equation does is it kind of measures how far you are, how far this new point is from each of these distributions. All right. So it's a statistical distance that you measure for this point with each of these distributions, and whichever is closer, you say it belongs to that class. All right. So and that is given by that distance. So that distance is actually called the Mahalanobis distance. Right. So if so, let me go back to some basics of geometry. Right. I assume all of you know what is a Euclidean distance. Right. So Euclidean distance can be computed for a pair of points, right? So let's say you have a two-dimensional space, right? You have a point over here and a point over here. Let this be mu, okay, mu1, where mu1 has two components, mu11, mu12. Right? This is mu11, mu12, and let's call this x star, and this is x star 1, comma x star 2, right? So the Euclidean distance between them is essentially just a summation x1 star minus mu11 square plus, so no summation, x2 star minus mu12 square and square root of this, right? I assume everybody knows that. That's just a standard Euclidean distance in a geometric space, right? However, with Mahalanobis distance, you do something extra, all right? So you could have done this here, right? You could have computed the means like this, right, using the MLE estimate, and then just computed the distance to the means, and whichever is closer, you call that as the correct class, right? But there is a problem there. The problem there is that what if your data looks like this? Let's say one of your classes, right? So the minus class is like this. So these are all the negative points. So it forms a perfect ellipse, but like this. Okay, and let's say your positive points are like this. positive points are over here. All right. Now let's say you get a new point, right? And the new point is right in the middle over here. Let's say this is my x star, right? So when you do MLE, what the MLE would do is that it will say that this is the mu, the second mu, that this is the mean of this distribution, and this probably is the mean of the first distribution. All right. If you just do a Euclidean distance, which is you just measure how far is this and how far is this, right? This might be smaller than this, right? But what you can see, I mean, intuitively, is that because the data is distributed like this, even a smaller distance between the mean and this seems to be higher because the data is naturally distributed in this direction and your data point is so far away, right? However, this one statistically is closer, okay? So by Euclidean, x star is closer to mu2, right? But statistically, if you look at how the data is distributed, x star is closer to mu1. Okay? So how do you measure the distance between 2 points? By also incorporating how the data is distributed. So that measure is called Mahalanobis distance. There's a very famous statistician from India, P.C. Mahalanobis. So this is named after him, right? So the Mahalanobis distance is the statistical distance between 2 points. So that is measured as, that is essentially measured as this, is x minus, so any 2 points. If you have x star minus mu1 transpose inverse x star minus mu1. All right. So if you look at Euclidean distance, right? So mathematically, Euclidean distance can be written as this. Even though I wrote a different formula earlier, right? But in the vector notation, it can be written as this. Right? It's the same thing as these both are equivalent. This and this. And if you expand it, it looks like this. Right? So what Mahalanobis distance does is it introduces this variance as well. So it not only looks at how far you are in the geometric space, but also weights you by the variance of the distribution. All right, and this is essentially what you use in the discriminant analysis. All right. So what happens then is that you compute the Mahalanobis distance between this and each of the means, and whichever is closest, you say that that is my true class. All right. Any questions so far? All right. So this portion will not be right. So we will not have discriminant analysis questions in the midterm. But as soon as you come back from your spring break, we will hit you with the second assignment, and that is where you have to look at this. All right. So that is where you will find this useful. So I'm going to stop here with the discriminant analysis. Any questions so far? All right. In fact, there's one more thing, which is let's see. Right. Okay. So there are two options in creating a discriminant analysis. Okay. So discriminant analysis, what you do is you estimate mu1, right, and sigma 1, and mu2 and sigma 2. These are the means and variances of these two distributions, right? And then you compute the Mahalanobis distance, right? Now there are two options. One option is in which you keep it like this. This is also called as the quadratic discriminant analysis. However, if we force sigma 1 equal to sigma 2 equal to sigma, if we make both of them equal, right, we can force it, then you can still have the same algorithm, and that is called linear discriminant analysis. Okay. Why is it quadratic and why is it discriminant analysis? Why is this linear and why is this quadratic is the answer that you will get when you do the assignment. All right. So let that be a mystery till then. Any questions so far? All right. So now let us move to a quick review. We have 25 minutes for the midterm. All right. So what I'm going to do is I am going to sort of switch over here and look at some of the gradients problems one by one. And I'm going to just sort of give you basic hints. But if you have more questions, please raise your hands and ask me, and then we can work it out in more detail. All right. So I'm going to go backwards. Of course, what I might have said this before as well, but the quiz that is out right now, right? You need to do this. I want you to work on these two before the exam, because you might get problems similar to this, right? So this is not, I mean, even though the deadline for this quiz is when the spring break ends, but for the midterm perspective, you want to look at these problems, right? But of course, I'm not going to work it out today. But if you look at this problem is very similar to the question that we did in the class, right? We did an example in which I had data something like that. In that, the data was more about, what was it? The tumor example, right? In fact, I have it here. Right. So if you follow how we solved this, I think we did this on Friday, you should be able to answer this question as well. All right. So that's the knife based classifier. All right. So one, and then this one is this one that we did just today, and I don't think you have to do this for the midterm at least, right? This one won't come in the midterm, because if you look at this one, this needs you to compute the densities and everything, so that requires more sort of computation. So I don't think I have questions like that here. All right. So that was all I wanted to tell about this quiz. So let's go to quiz number 5. And this, I think the TA did a little bit of it earlier, right? So this one is interesting, right? So this one, and I got a lot of questions about this. So the issue here was that the way this question was posed, it was slightly different than what you've seen so far, but essentially the idea was the same, right? So instead of giving you the actual training data, what we did was we already counted up all the possibilities. And that was kind of what was throwing many of you off. So you want to be careful about that. If you see, not just in midterm, but in real life, right? Sometimes you might get the training data itself, right? You would explicitly list out, okay, the first example was A, second was B, was this, right? But whenever we talk about categorical attributes, right, a lot of times you might just get the counts. But you can do the same analysis with that as well. So if you look at this example, I'm talking about the second one here, is we could have posed it in two ways, right? So what the question here was that your CX, the classes, you could have 4 classes, 0, 1, 2, and 3. So think of it as 4-sided dice with 0, 1, 2, 3 written on it, right? So typically in the class, whenever we have seen training data, we have seen it like this, that the first time you observed a 0, and the class observed a 0, second time you observed a 1, then a 0, 0, 0, 1, 1, 2, 1, 3, 0, 1, 2, and so on, right? And then you had to do the estimation and everything. In this problem, what we had done was we had already counted up the zeros and told you that there were 5 zeros, 5 ones, 2 twos, and 1 3, right? So it's the same training data, but given in this form. So don't get confused when you see things like that. Sometimes we might just compute these. Sometimes I could have also given you that just the probability. Sometimes I could have given you that we saw, so 5 by 13 times or the fraction of zeros was 5 by 13, and the fraction of ones was 5 by 13. Fraction of twos was 2 by 13, and 1 by 13 of threes, right? So it is again the same data, but in fractional format. Because if you look at naive Bayes, how that works is that you don't really need to have this data explicitly listed out, right? All you need actually are the proportions. So I could have, instead of this, just given you that this is a different data set where I would say that 20% of the times I saw a 0, 10% of the times I saw a 1, and 30% of the times I saw a 2, right? So you automatically know that 40% of the times you would have seen a 3 because they all need to sum up to 100%, right? So this is essentially, the variation here is just how we present the training data to you. And that happens in real life as well. In fact, most of the statistics, if you look at any statistical analysis, so if you take a statistics course, most of the times they would not list out the data. They would just give you the counts, which makes sense. Yeah. Right. So, yes, exactly. But what, yes, it's a fraction of. But the thing is that I might have also given you just this, or the actual values here. So I could have given you that point, the fraction was 0.5 of zeros, 0.3 of ones, 0.2 of twos, and zero point 0.2 of threes, right? So now you don't know how many total there were. But the thing with naive Bayes is you don't need that. If you look at how the equations write out, right? You don't really need how many total were there because you just need the relative proportion. Because if you remember, right? So if I want to find, okay, what is the probability of the class to be so in this example, at least in the gradients quiz, I wanted you to compute the likelihood, right? Likelihood of this data set given class is 1, right? So how do you do that? You just say, okay, the probability of 0, what is the probability of 0 given class is 1, times probability of 1 given class is 1, and so on, right? So then, so explicitly it's like this, but you can club it like this. You can put all the zeros together and say it is probability of 0 raised to however many zeros I had. So let's say there were A zeros times that B. Right. And we have given you these things, right? Individual things. And for different values of A, B, C, and D, you had to compute the likelihood. Right. Right. Sure. So you don't know the total number of observations, but you know the relative proportion, right? So in that case, you can, because you just need to compare, right? You need to compare the D. So you might not be able to compute the exact likelihood, but you can compare D, let's call it L1 and L2, because this would be, instead of, it will be A over whatever N. Let's say the total number of attributes, you assume that, let's say the total number of observations were N, okay? So if I give you 0.5 were zeros, then you would write it as P C equal to 1 raised to NA, because those would be the number of things, and then times everything, right? So you can express L1 as a function of A, B, C, D, and N, but N would be common in both. So you can compare, because you just need to compare which one is higher likelihood, right? So that's the point. So that's a good question, right? Any other questions about this one? Okay. And this problem is fairly simple, right? This is exactly following all the parameter estimation for beta distribution, for Bernoulli distribution, right? So always remember those 4 expressions. Whenever you have to estimate the parameters, right? Always remember that if you compute a prior using just a prior, then it is going to be A over A plus B. If it is just the MLE, then it is number of heads divided by total number of trials. If it is a map, then it is going to be a plus nh minus 1, a plus b plus n minus 2. And if you are taking the base averaging, then it is a plus nh over a plus b plus n. But do go through the notes and see how do we derive this, because we have gone through the rigorous process of actually coming up with these expressions. So these are not magical expressions, right? However, to solve problems like the ones like this one, yes, right? Oh, yeah, 0.2, right? To compare the both values. Okay, you'll be going back here. All right, so this I'm assuming is easy to do. All right, let's go to 4. This one is interesting, and we did go through this. So for these kind of problems, this is actually not a machine learning problem as such. It's more of a statistics problem, right? But this is sort of a basics that you need to know, right? So the 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 main way to solve these problems is to express the probabilities and events correctly. So what are your events, and what are these numbers telling you, right? So for example, in this one, the way you do it is that you have two types of events, right? One event is that the event of you testing positive, all right? It can take two values, true or false. So you either test positive or you test negative. And the second event is the event that the machine or the test is accurate, right? So it's either a good test or a bad test. So you have two, no, sorry, I'm sorry. A disease or not. So the second event is, do I have a disease or not, right? So you have two events, and then you need to express these probabilities as that. So because all of these are kind of like conditional probabilities, but the thing that you want to be clear about is what is dependent on what. So for example, when I say the test is 95% accurate, that when tested on 100 patients, it identifies 95 of them as positive. So as a probability, the way to write it is that this is probability of me having a disease. I'm sorry, probability when I actually have a disease, because that's how we measure the accuracy, right? So probability that that the test will give a positive result when I have the disease. So you express it that way. Then the same thing, this is other way. The probability that a test is positive when I do not have a disease. So now you have these probabilities, and now what you can do is you can now what is being asked, right? So assume that you have tested positive. Which of the following is true? So in this case, what is it saying is there a close to 1% chance of actually having the disease? So what you want to compute is probability that I have the disease given I have tested positive, right? So you can apply the Bayes rule and get the answer. So let me express it here quickly. So what is being asked is, what is the probability of me having disease given that I tested positive, okay? So this is the probability that you have to compute. Now you can compute it using Bayes rule by saying probability that I tested positive given me having disease times probability of me having disease as a prior, right? This is a prior probability divided by the whole expression. I assume you know the whole expression. So now the only thing that is left is plugging in the values, right? This is 95% because that's given from the question, and this is the prior probability. So it is said that it is a rare disease, right? So rare disease means that 1 in 100. 1 in 100 chance. That means that without knowing anything, the probability of anybody to have a disease is 1 over 100, right? So now you can plug these values and compute it, okay? Any questions so far? So it's basically trying to read the question, which would be written in normal English, and converting it into the actual probability. All right. This one I'm guessing is fairly easy to do because we have gone through this example very closely. No takers for this, so I'll move on. Let's look at this one. This one, of course, was, I mean, once you have done the assignment, right, I'm sure you can do this very easily, right? So all you were asked to do here is to do the feed-forward loop of a multi-layer perceptron, right? So these are the two inputs, right? So these are your x's. These are the weights for your hidden unit. So each hidden unit, of course, will have two weights, right? Because there are two inputs coming in. Here we are ignoring the bias. Ignore the bias for this example, right? And then, so what you can do here is you can do the W transpose X. So W transpose X is 0.1 times 0.35 plus 0.8 times 0.9, right? And then you take the sigmoid, that's the activation. That becomes the output from here. And same way you can compute the output from here. So now you have two outputs. Then you compute, now this is the output unit. Here there is only one output unit. It will have two weights, right? Because there are two inputs coming into it. So these are the weights. So you compute the W transpose X here, or W transpose Z here, and then you do the sigmoid of that, and that becomes your output, right? So that's the, I mean, that's exactly what you did for your assignment as well. All right. Now here what was asked was the error. All right. This error is that delta that we computed. Now delta error is basically the difference between the output and the input. Right. So delta is, if you remember, your delta L's were YL minus OL, right? Y minus O. Because here you only have one Y. Y is the true value, and O is the output that you get. So you just compute Y minus O, and that would be the error. All right. That would be the error at the output node, right? And then the error at the hidden node would be when you move back. That's your delta K's, I think. Delta J's, right? So delta J here would essentially be, if you remember, is just the summation of all the errors here times the weights, right? And you bring it back here. So that's how you have to compute it. So you just need to follow the, I mean, I would suggest that you have a copy of either those expressions in the exam. I'm not saying there will be a problem like this, but if there is, all right, okay. Now these are the problems about perceptrons. Now perceptrons are sort of the easier cousins of neural networks, so you can do that easily, right? So perceptrons only have the output unit. So all you need to do is take your inputs, do a transpose X with the weights, and here you just need to do the summation, right? So there is no sigmoid here. And then this means that you just need to do a thresholding, that if it is, and threshold is given to be 0, right? That's kind of the bias, right? Exactly. That is the bias. That's the, see, in the case of perceptrons, we can express it as W transpose X greater than theta. So this is that theta, right? If you incorporate the bias in the input itself, then it's W transpose X greater than 0. But here I'm explicitly saying that these are the 4 inputs and this is the output. All right. Now here, what in these problems, I think even the next one, they're simpler than usual in the sense that all of your inputs can only be binary, right? Which means that you can only have, these are 4 values, so you can have 2 power 4 possible inputs, right? Some of them will be positive, some of them will be negative. So instead of giving you the training data, right, I could have given you the training data in which I would have said that for this input, the class is this input. I give you a general rule. So for example, here we say that the general rule is if 3 or more inputs are +1, then it is positive, otherwise it's negative, which means that out of those 16 examples, right, 16 possible examples, some of them will be positive. The ones that will be positive are the ones in which you have 3 ones or 4 ones. So if you have 1, 1, 1, 0, that will be positive examples, 1, 0, 1, 1 positive, and 1, 1, 1, 1 will be positive, and everything else will be negative. All right? And that's it. After that, you just need to follow the perceptron algorithm to learn the weights. This is just right. Because if you remember the perceptron algorithm, right, there's a lambda parameter here with which you update your weights. That just you need that. Any questions about that? for this one. You just need to follow that. No, um, right. Well, if you look at our right, yeah, I think in the slides I've explicitly mentioned it here. This is the expression for the error. So at the hidden unit number 1, right? This will be O1, which is the output going out of the hidden unit 1, 1 minus O1 times the summation of all these things. Now in that example, it's much easier because you have only one, your K is 1, there's only one output unit, which means that it is essentially whatever output came from here times 1 minus output times the weight here times the the weight on this edge times the error here, right? So that's kind of just the back propagation. So follow these expressions to do that. Any questions about that one? All right, fantastic. All right, I have what, 4 more minutes. So let me quickly go through this. All right, so we've done this one. This one is again very easy, just the perceptron. And this is again perceptron. So those I would assume you should be able to do very easily. This one you don't have to worry about it. This is a little too involved, so this is not covered. So I'm not going to spend time on that one here. And that's it. And then this is the one. Now here, these are the problems which you want to practice a little more. So when you go back, what you want to do is you pull out the notes, right? And there you have the exact algorithm, right? So you will have the candidate elimination algorithm. See if you can follow it step by step. Now, one thing that I can tell you is that you don't have to memorize the algorithm, right? Because if there is any algorithm that I want you to follow, it will be there in the problem itself, all right? So you don't even have to bring the notes with the algorithm on it. So we will give you all the algorithms which you need, right? So it will be a self-contained exam. But what I need you to do is to be able to follow the steps one by one. So what I would suggest is when you go back, right, you try to do these problems again and again, right? And even the problems that we solved in the class as well. So if you could just say, okay, here's my data. Let me go through each step of the candidate elimination. Same way here is my data and here's my algorithm, right? The algorithm is pretty easy. Every time you take one item and then you do that, right? You want to be able to do that again and again. So in the exam, I could change the algorithm a little bit. Like instead of this step, I can make it the other step. But the basic process will be the same. So if you are familiar with how to follow these, you should be able to do that. All right? Any other questions? Yes. Practice questions. Yeah, I could. So what I can do is maybe create another gradients quiz. It won't be graded, but it would have some other questions as well. So you can. That quiz you can take any number of times. So I'll probably be able to do that by end of today. So end of today you'll have a quiz, practice quiz that you can take, and it will have maybe a few more problems that you can attempt. All right? Any other questions? Yes. Right. No, no. And but you don't have to do that. At least what I can tell you is that for the exam, I won't expect you to compute exp of anything. So I could change, but I could change the activation function, right? Instead of exp of z, I can make it z to the power 3 or something like that, right? So, but you won't have to have a scientific calculator.